All right, this is Mr. Ainsworth, and we're going to get into cool activity dealing with exponential growth and decay problems. And recall our general exponential function, y equals a times b to the x power, where x is in the exponent. Yes, x is in the exponent. That's one of the reasons why they call this an exponential function. Okay, remember there are two types of exponentials here. The growth function, where the base is bigger than 1. All right, and you have 1 plus r here in the base, and the decay function where it's 1 minus r, where the base here is less than 1. So let's go through the different terminology here before we get started, because you got to remember what all these variables mean. I mean, that's half the deal in mathematics, right? You got to figure out what all this stuff means. So here we go. A sub f. Everybody say A sub f. All right, that's the future amount. A for amount, F for future, right? Amount of in the future, or future amount. A sub I, all right, that's the initial amount. And what do we mean by initial? Well, I mean the starting amount. Okay, starting amount. So go ahead and put that in. Initial, starting, same thing. I don't care whether it's a growth or decay problem. A sub I is the starting amount right here. R, well, that's just the growth or decay rate, depending on what problem we are working with. It's always written as a decimal. All right, remember that. I see many people forget that R is a percentage. Yes, okay, but you got to convert it to a decimal. And then T stands for the number of time intervals of the growth rate. Sometimes it's years, sometimes it's days. In this activity, we're going to really change it up so you really start to understand what this exponent means. It's the number of time periods that have passed. It could be days, weeks, hours, months, years. Well, we're going to get involved here so we can try to understand what's going on. All right, and then we're going to take a look at a lot of different situations here so you get some experience. All right, so let's take a look at the first situation here. A dish has 212 bacteria in it. Okay, this could be a petri dish like you see in science classes. The population of bacteria will grow. Okay, this is a growth situation. All right, grow plus 80% every 2 days. Now right here I can already see that R equals 80%. That's the growth rate. All right, and as a decimal that's let me write that a little bit better. 0.80. You got to shift the decimal twice to the left. So the growth rate, okay, which is R, is 0.8. All right, now the number of intervals, or the amount of time that expires or that passes that it grows 80% is every 2 days. So let's underline that because that is very important to the situation. The question is, how many bacteria will be present in 4 days, and then 8 days, and 11 days? All right, so I'll tell you what, have your calculator nearby because we're going to need it. So turn that on, power that up, and it doesn't have to be the TI-84, it can be any calculator, okay? Because any calculator can calculate all this stuff. Just have a scientific out and ready to go. Pause the video if you don't have one, go get it, and then play it when you're ready. All right, so here we go. What we're going to do is I'm going to do one problem by hand just to show you what's going on, and then I'll show you the way we should be approaching all of these problems here using the growth and decay formulas up top. All right, so first of all, we start off with 212 bacteria. This is your A sub I. Your A sub I is 212. This is the starting amount. Okay, so first of all, you have to understand that much of the problem. You have a starting amount of 212 bacteria. It's going to grow 80% or 0.8 every 2 days. Okay, so what we're going to do is we're going to have the number of intervals here. And then we're going to do the number of days here, and then we'll do the number of bacteria here, number of bacteria. So in the beginning, at interval 0, or day 0 here, 0 days, we have 212 bacteria. And after one interval, all right, or 2 days, okay, because it says every 2 days this thing grows by 80%, we have not just 212 bacteria, but 212 bacteria plus 80% more, which means we have 180% of what we started off with. So I have 180% of 212, and you have to remember that 180% as a decimal, all right, is 1.80. All right, 100 plus 80 equals 180%. That's where I got the number 180 here. Take 180 divided by 100 and you get 1.8. You can verify that on a calculator if you want. All you have to do is go 180, all right, divided by 100 and you get 1.8. Just shift it 2 places to the left. It's a lot easier. Okay, so I have to multiply it by 1.80 to get that new, the number of new bacteria. Okay, so 212, enter that in. Let me clear it out and start fresh here. 212 times 1.8. That gives me about 381.6 or 382 bacteria. So 382 bacteria after only 2 days. Again, this is days now. After one time period or interval. Well, 2 more days pass, another time interval passes, and that's a total of 4 days. The question is, how many bacteria? Well, you just keep multiplying it by 1.8 because we have 80% more. 100% of the original plus 80% more, that's 180% or 1.8. So since we already have that on the calculator, well, we just take the answer here and just go times 1.8. Don't need to rewrite it because the calculator takes your previous answer and multiplies it for you. And you get about 100 or 687. You got to round up here. Okay, 687. So there's our answer, 687 bacteria after 4 days. So there's my answer right there, because I want to figure out how many bacteria after 4 days. But you got to be thinking there's got to be an easier way rather than just do it per day, because what happens if I ask you how many bacteria after 600 days? You don't want to repeat this that many times. All right, so let's learn how to use your growth formula, okay, up at the very top. And I'm talking about this one right here, your growth formula. So my future amount after 4 days, your A sub F, is going to be your initial amount, A, which is, in this case, 212, right? 212 times 1 plus R, but I told you that R is 0.8, right? So 0.8 to the T power. Now, T is the number of time intervals. Now, how do you get the number of time intervals? Well, you know we did it. We wanted 4 days overall, right? So after 2 days is 1 interval, and after 2 more days is 2 intervals, or 4 days. What's an easy way to calculate that? The time interval of 2, because I need to raise it to the second power here. Well, that's simple. You just take 4 and divide it by 2, and you get 2. After 2 intervals, or 4 days, you have 687 bacteria. So T, this is T now, all right? I'm talking about this right here. Number of time intervals is always, you've got to take the total amount of time that you're considering here, divided by the interval of time that it grows, and it grows 80% every 2 days. So I got to take 4 divided by 2 and I get 2 intervals. Now watch this on the calculator. I'm going to get the same answer, but in this one single calculation, I'm going to take 212, multiply it by 1 plus 0.8, which is 1.8. Just type in 1.8 instead of 1 plus 0.8. Raise it to the second power, okay, or you can hit that squared button and hit enter. And notice that we get the same value. So about 687. So 687 bacteria after 4 days. After 4 days. And that's the fastest way. And this is the way that you want to handle the situation in all of these cases in here. You don't want to do it day by day like I've done in previous lessons here. You want to be smart about it and use the growth function or decay function depending on what's going on. Let me show you one more time. Now, in 8 days, how many time periods have passed? Well, the number of intervals or time periods is, we know that it increases 80% every 2 days. So T, in this case, is going to be 8 divided by 2, or 4 time periods or intervals that have passed. I'd have to do this 2 more times to get to 8 days, right? But I don't want to do that. I want to be smart about it. So I take the future amount, and in this case, it's going to be the initial amount times 1.8, the growth rate again. This is the growth rate, or excuse me, 1 plus the growth rate, to the 4th power, because there's 4 intervals or time periods that have passed to reach 8 days. So 0 to 1 time period for 2 days, 2 more, 4 days, 2 more, 6 days, 2 more, 8 days. That's 4 intervals or time periods. Okay, and what is this equal to? I don't know. Let's figure this out. So I take 212, raise it to the 1.8 power, times 1.8 to the power of 4, to the fourth power, because there's 4 periods here, and that's about 2,225. 2,225 bacteria, all right, after 8 days. There we go. Got to spell bacteria, right? All right, there we go. After 8 days. Okay, well, how many after 11 days? Well, T in this case is, let me see, 11 days divided by 2 will give me the number of time periods or intervals. And 11 halves is 5.5 or 5.5. Just check your calculator. Just take 11 divided by 2 and you get 5.5. So 5 and 5.5 intervals, all right, or time periods. So now my future amount is going to be 212 times 1.8 to the 5.5 power. Well, on the calculator, this is no big deal, guys. We take 212 times 1.8 to the power of 5.5. No big deal with this. We know it's increasing because it's a growth situation. 5,374. 5,374 bacteria. Notice how it's increasing really fast. I mean, I over doubled that right there from 8 days to 11 days. Okay? So pretty big increase right there. And that's what we mean by growing exponentially here. Oh, by the way, this is a video, keep in mind. So if you need to rewind and listen to me again and in order to understand what's going on, pause and play, rewind as much as you want. All right, you go at your own pace, and remember to use that pause and play button as much as you want. Okay, so let's read this next situation here. The house down the street has termites in the porch. Oh my God. The exterminator estimated that there are about 800,000 termites eating the porch. You gotta love how they figure that kind of stuff. That right now, that's a starting amount. All right, right there, I can already see A sub I. The initial amount. This is the starting, all right, amount, AMT. He said that the treatment he put on the wood would kill 40% of the termites every day. That's important right there, so underline that. This right here, let me see, kill. That means 40% die. That's decay situation. So right away, this is decay, okay, or loss. All right, we lose, or these termites die at 40%, so you don't have as many every day, right? Because that's why you pay these guys to come on in, is to kill the guys, so there's less of them the next day. You don't want them to grow, you want them to decay or go down. All right, so right away, I know this is the decay situation. I have to use a new formula here. I have to use A sub I times 1 minus R to the T power. Because it's a decay situation, I have to subtract the growth rate from 1. Okay, well, I know that here 40% here is equal to 0.4. So let's set up this problem. Let's figure this out. Now, it's every day. This is super important. Every day. So now, the T, the time periods, here in this case, after 3 days, is 3 divided by 1, because every day means every 1 day here, which is a total of 3. So here the time, or T, represents 3 in this case. After 3 days, there's 3 time periods, or 3 intervals that have passed. So now my future amount would be the initial amount, 800,000. That's how many you start with. That's a lot of termites, man. Times 1 minus now, because this is they're killed off. Okay, so it's a decay situation or a loss. 0.4 raised to the third power. All right, let's figure this out. So in this case, we've got 800,000 times 1 minus 0.4, so times quantity 1 minus 0.4. And you could type that in if you want, or you can put in 0.6, guys, because 100% minus 40% is 60%, which is 0.6. 1 minus 0.4 is 0.6. If you want to put in 1 minus 0.4, be my guest, but you can just put in 0.6, raise it to the third power, and we're good to go. Okay, notice there's not as many there, okay, because you only have 60% remaining. All right, on the first time period, and another 60% remaining on the second, and the third you have even less. So it's really gone down quite a bit, 172,800. So 172,800 termites. I gotta spell this right, don't I? Okay, termites. There we go. Okay, now how many after 36 hours? Well, how many days is that? So 1 day, okay, equals 24 hours. All right, half a day is, let me see, half a day is 12 hours. So this is a day and a half. So this is equal to 1.5 days. That's 1.5 time periods. So in this case, t is 1.5. So here we go. So the future amount is, again, the starting or initial amount times 1 minus 0.4 or 0.6, all right, raised to, in this case, 1.5. 36 hours is 1.5 days. 24 hours plus 12 hours is 36 hours here, which is 1.5 days. One day is 24 hours, half a day is 12, and that's obviously 1.5 days. So let's do it on a calculator. Here we go. 800,000, gotta put the right number of zeros in there, there you go, times 1 minus 0.4 or 0.6 raised to the 1.5 power. Whoops, I must have put it in wrong. Oh yeah, it really helps if I put in the right decimals here, 0.4. Let's redo it. All right, there we go. About 371,806. So 371,806 termites in this case. Okay. Now after 2 weeks, let me see. 1 week equals 7 days. So this is 14 days. Oh boy, watch what happens here. So now, what's my future amount? Well, 800,000, always the starting amount, times 1 minus the decay or loss rate to the 14th power. Here we go. And problems look like or like this look intimidating, but with the powerful power of the calculators here, guys, it's no big deal, man. We could take it to any power we want. All right, and we have about only 627 left. Okay, 627 termites left, which is good for you if this is your house. Okay, and started off with 800,000. After 2 weeks, you only have 627 left. You're looking good. This is a good thing. All right, that's why people hire exterminators here, because if they can say that, hey, 40% of the termites is killed every day if they keep on applying the stuff, well, that's a good sign, because termites eat your house away and destroy the wooden structure of the house. And so this is a really, well, termites are a bad thing, but the treatment, the exterminator, is a good thing, okay? All right, so pretty cool here. We just use, we first use the growth formula, now we use the decay formula. What's next? Okay, let's check this out. In June, the 5th grade class starts out with a starts out, look at that, started out. Don't you think that's an important word? Okay, so what do you think that 10 millions represents? Is that A sub F, A sub I, R, or T? Tell the person next to you. Or if you're alone, say it out loud. That's right. It's the A sub I. Okay, we start off with 10 mealworms. All right, these squiggly guys. Ooh, yeah. All right, mealworms. Wouldn't you want to eat those guys? All right, the population of worms will double. Ooh, double. That's a growth rate of 100%. So R is equal to 100% or 1. That's what it means to double. All right, you have 100% more the next time. All right, every month. Let's underline that. That is important. Every month. How many mealworms will the class have for their experiment in 3 months? Well, T is the number of intervals or time periods. Okay, so after 3 months and it doubles every month, then that must mean that T is 3. So what's the future amount? I don't know. Let's figure this out. Now this is a growth rate. So in this case, your function looks like this: A sub I times 1 plus R to the T power. Now it's a growth, so you add. Okay, add the rate instead of subtracting. If it's a decay, subtract. If it's growth, you add. So the future amount in this case Well, we start off with 10 mealworms. The growth rate it doubles, so 1 plus 1 raised to the third power, because after 3 months have passed, there's 3 time periods of 3 intervals that have passed. So what is this? Well, this is 10 times 2 to the third, and that's 10 times 8, all right, or 80. All right, there's 80 mealworms. Now, if you didn't want to use your head, you could use a calculator, I suppose. Let's clear this out. 10 times 2 to the third power. Well, voila, you get 80, right? So I try to use my head as much as possible. If you don't like doing that, well, I guess you can use a calculator. Okay. Well, how many mealworms after 1 year? Well, we know there is 12 months in a year, right? So T is 12. So in this case, my future amount is 10 times 1 plus 1, or 2, because this is a doubling situation. Let's highlight that. It's a doubling situation, raised to the 12th power. Well, suppose you don't want to take 2 to the 12th in your head. Well, 10 times 2 raised to the 12th power. All right, that's big. You guys remember the doubling, the powers of 2 drill that I do with you guys? 2, 4, 8, 16, 32, 64, 128, 256, 1024, and so on. And you'd have to do that 12 times, then multiply by 10, and you get 40,960. So 40,960 mealworms. Oh yeah, that's a lot. Okay, the question is how many mealworms after 45 days? Now I know that there's 30 days. Well, actually, let's assume that when I say every month, it means every 30 days. So let's make this assumption here, every 30 days. Right there. Let's make that assumption. So it doubles every 30 days. Let's make that assumption. Question is, how many time periods have passed? Well, 40 divided by, excuse me, not 40. 45 divided by 30. Well, that's 1.5. And if you don't believe me, just do it on your calculator. 45 divided by 30, that's 1.5. So 1.5. So that's T, the number of time periods or intervals that have passed. So now my future amount is how many I start with, A sub I, which is in this case 10 mealworms, times the 1 plus R, which is 2. All right, it's doubling, guys. This is a doubling one. So the base is 2, and raised to the 1.5 power. So let's figure this out. So we got 10, all right, times 2 raised to the 1.5, or 1.5 power. That's about 28. All right, so 28 mealworms. Now, it's less than 3. T was less than, or it's half the amount of time, and you can't just take 80 divided by 2, but because it's not linear here. But it's got to be less than 80 because we're talking about 1.5 time periods versus 3. After 12 time periods, man, you have a lot more. So these guys really increase fast. All right, any doubling situation increases very fast, as you guys found out. Okay, check this situation. Your baby brother has an ear infection. The doctor said there are probably 50 million. This is 50 million. All right, bacteria in his left ear. That's a lot. This is not good, guys. All right, the penicillin that the doctor prescribed will kill 7% of the bacteria every 6 hours. Ooh, will kill 7% of the bacteria every 6 hours. Let me highlight every 6 hours. Now, the word kill is important too because this is a decay situation and not a growth situation. If it kills off 7%, then you're not going to have as many left over. And that's what penicillin is for, is to kill off the bacteria. So right away, seeing this right here, I know it's a decay situation and not a growth situation. So that's the very first thing you need to figure out. So my formula looks like A sub I times 1 plus R to the T power. Because, excuse me, 1 minus R. Let me switch that. 1 minus R. Because it's a decay situation. Okay? Put in the sound effects. Now, I know the 7% is the decay rate. So R is equal to 7%, which is 0.07. This is the decay rate, or rate of decay. Now, every 6 hours, that's important. Every 6 hours. This is, underline that. That is super important. The question is, how many bacteria left after 1 day? Which means you need to know how many hours in a day, guys. So 1 day is 24 hours, right? You guys know that. Well, T is 24 hours divided by how many hours that it takes for the bacteria to be killed off by 7%. So I know I start off with, I want to know what happens after 24 hours, but how many time periods or intervals has gone by? Well, let me see, count multiples of 6. So I go 6, 0, 6, 12, 18, then 24. If you use your fingers, 0, 6, 12, oh, excuse me, 6, 12, 18, 24, there's 4 time periods because we know that 6 times 4 is 24, or you can just take the number of hours in a day, 24, divided by 6, and you get 4 time periods or intervals. That's T. Intervals, and I keep saying time periods because that's how I was taught, time periods. All right, so what's going on here? The future amount is the initial amount. What's the initial? Oh, right here. Okay, that is A sub I. There's 50 million to start with. So 50 million times 1 minus 0.07, because this is a decay situation. And after 1 day, there's 24 hours. If this thing happens, or if 7% dies off every 6 hours, we've got to divide it by 6. So 24 divided by 6 is 4. We've got to raise it to the 4th power. So the T, the time periods, the number of time periods here, number of time periods is very important. You'll notice that I figure this out before I even start the problem, because I can't even set it up properly unless I figure it out. And then once I figure it out, then I can go for it. So I'm going to enter in 50 million. One, two, three, four, five, six, 7. Yep, okay. That's 50 million times 2 to the, well, not 2, go back. 1 minus 0.07 raised to the 4th power. Now you should always double check your digits here, because 1 digit off and you're toast, right? So always check your arithmetic here. All right, and so there's 37,402,600.5 bacteria. So 37,402,000. So 37,402,600. Well, I'm going to go 0.5. I'm going to round it up 1. All right, bacteria left, okay, after a day. So how many are left after 5 days? Well, let's see here. How many hours in 5 days? So 5 times 24. Let's use our calculator to our advantage. 5 times 24. There's 120 hours. So it's 120 hours have gone by. Well, every hour is how many time periods do we have if this thing happens every 6 hours? So I take 120 divided by 6, and well, I get what, 20? So 20 time periods. So now my future amount is 50 million times 1 minus 0.07 to the 20th power here. What's that? I don't know. Let's figure this out. So enter in 50 million. 1, 2, 3, 4, 5, 6. That's 50 million times 1 minus 0.07 raised to the 20th power, or 20 time periods. And I get a lot less. I get only 11,711,000. So 11,711,943.7, or 944. So 944 bacteria left over. So it's decreasing. As you can tell, we start off with 50 million. Then after 1 day, we have 37 million. And then after 5 days, we have 11 million. So we're doing better here. Hopefully your baby brother gets better here, because the bacteria is going down. All right, now after 1 week, well, that's 7 days, right? So after 7 days, that's 7 times 24 hours. What's that? So 7 times 24 hours, that's 168 hours. So 168 hours. So what's T in this case? Well, it's 168 divided by 6. Again, this number is so important here, guys. Divided by 6. So let's take it and divide by 6. That's 28. So there's 28 time periods have passed. Or you can say intervals, okay? So what's my future amount? 50 million times the quantity 1 minus 0.07 raised to the 28th power. It should be less than 11 million, right? Because we're talking about 7 days versus 5 days. So let's figure this out. 50 million, 1, 2, 3, 4, 5, 6, times 1 minus 0.07. Uh-oh, that was a mistake, 0.07. Gotta be careful with that right there. I put in the wrong decimal, and again, garbage in, garbage out. So on the calculators, you gotta put in the right values. Make sure you double check your numbers here. If you are expecting a smaller number, which I am, I better get one. So here it is 6,553,000. So 6,553,791. So 791 bacteria. That's after 1 week. Well, how about after only 3 hours? Only a very short period of time. Well, that's half an interval here. So 3 divided by 6 is 1/2. So if it's a very, very short period of time, what do we have? We probably still have a lot. Because it takes time for things to take an effect, right? I mean, that should make sense. You know, you've been to the doctor before. Okay, so let's figure this out. 50 million, 1, 2, 3, 4, 5, 6, times quantity 1. Whoops, going to go back here. I got to put a minus sign. Make sure, again, you punch the right thing. Take it to the half power, 0.5. Look at that. There's 48 million left, okay, because it takes time for it to work. 48,218,000. 48,218,000. 50, I gotta read this right, 54. So not very many bacteria have gone after only a half an hour because there's only, or 3 hours, because only a half a time period has gone by. It takes time for the medicine to work, guys. All right, so make sure you take your medicine, do it, exactly the way the doctor prescribed, and over time it should help. You guys, this is really what happens in reality. This is what happens in your body over a period of time. I'm not just making this stuff up. This is real stuff here. That's why I like this section here, because it actually makes sense. All right? We can relate to it because it really does happen. All right, number 5. The population of Sukasuna, New Jersey, wow, I mean, that's a heck of a city there, was 11,171 in the year 2000. The estimated population growth is 2.1%. There's your growth rate right here. R is 2.1%, and that's 0.021 as a decimal every 4 years. Let me highlight that. Every 4 years. Super important. So already, I know my growth rate right here. I know my time period right here in year 2000. That is probably, this is going to be my A sub I, my starting amount right there. In the year 2000, this is my reference year. The question is, how many years have elapsed or has gone by from 2000 right here, this one right here, to 2020? So let me see, 2020 minus 2000, 20 years have gone by, all right? Now, every 4 years, the population growth is 2.1%, which means it increases 2.1% every 4 years. But the question is, how many time periods have elapsed? So once again, here we go. T is equal to 20 divided by 4, all right? And that means there's 5 time periods have passed by. There's 5 time periods. Okay, so what's my future amount? Well, A sub F is equal to my initial amount, right here, my initial amount, which is 11,171 times my growth rate, 1 plus now, got to add here, 2.1% or 0.021 raised to the number of time periods. And after 20 years, well, there's 5 time periods because it grows every 4 years, this percentage rate. So we're going to raise it to the 5th power. At that point, you're ready to go for it. 11,000, let me clear this out on this new problem, 11,171 times 1.021 raised to the 5th power. Double check your input, because again, good input, it usually gives you good output on these things. So 12,394. So 12,394 was the population at that point. Obviously, it got bigger, right? I mean, it started off at 11,171. It grew because of the growing situation. All right, this is a growth situation, keyword growth. So in general, it's a sub I times 1 plus r raised to the t power for a growth situation. Okay? All right. Now in year 2001, well, that's only 1 year out of 4. So t here, 1 year has gone by, but every 4 years it does this. It grows 2.1%, so it's a fourth of the time period. So in this case, it's not going to be very much. 11,171 times 1 plus 0.021 raised to the 1/4 power. Okay, so let's do this. So 11,171 times 1.021 raised to the 1/4 power, which is 0.25. So raised to the power, quantity 1 divided by 4, or you can put in 0.25. And as you can tell, it didn't grow very much because guess what? It's only 1 year later. And it does this every 4 years, not every year. So it's, it doesn't grow very much. So 11,229 roughly. So 11,229 people after only 1 year. Okay. Okay. Right now it's 2014. So let's see. T equals, in this case, 2014 years have gone by, but every 4 years it does this. So 14, well, let's use your calculator. I mean, what the heck? I mean, it's 3.5, but 14 divided by 4, you'll see what I'm talking about, 3.5. So in this case, T is 3.5. There's 3.5 time periods that have passed. So my future amount here would be 11,171 times 1.021 raised to the 3.5. All right, but what's that? I don't know. Let's got to figure it out. So 11,171 times quantity 1.021 raised to the 3.5 power. That's about 12,014 people. Okay. Now at the next century. Centuries every 100 years, I think. So at the beginning of the next century, so 2,100 here. So 100 years have gone by. All right, well, T here is 100 years divided by 4, or 25 time periods. So in this case, it would be 11,171 times 1.021 raised to the 25 power, because, well, there's 25 intervals in 100 years in this case. Okay, so let's figure this out. So we got 11,171 times 1.021 raised to the 25th power. All right, and that's about 18,782. 18,782 people. Let me double check that. Oop, I wrote it backwards. How about 82 people here? There we go. Okay, let me just triple check that. 18,782. Then good. That's after 100 years. So these growth formers and decay formers can be used in a variety of different situations, my friends. I mean, we're talking a lot of different situations here. Let's take a few more here. This year, estimated 4,324,000 people live in the country are illiterate. That means they cannot read. Cannot read. That is bad, okay? With new incentives and funding, the country is hoping to cut that number, cut, keyword, by 11% every 3 years. All right, let's highlight every 3 years. That's important. Now, if you're going to cut it by 11%, that means this is a decay rate. So the decay rate here, R, decay rate R is equal to 11% or 0.11. That means that my function in this case looks like a sub I times quantity 1 minus R raised to the t power because of the word cut. Let's highlight that. It reduces, okay, by 11%. The big question is how many people do you predict will be illiterate in the following years? Year 2035 and then the year 2095. Well, I don't know, man. Let's figure this out. So here we go. This initial amount right here, that's a sub I. That's your initial amount, 4,324,000. So let's see here. How many years have gone by? So this is this year. What is this year referring to? We're going to have to make an assumption here. We're going to say this is I don't know who made this document when, but we're going to have to make an assumption. So this year is 2014. Now, how many years have gone by? Well, 2035 minus that. So 2035 minus 2014, 21 years. So in this case, we've got 21 years divided by 3. That means 7 time periods have passed. Okay? So what is my future amount? So we take the initial amount, 4,324,000 times 1 minus now, because this is a decay situation, 1 minus R raised to the 7th power. So let's figure this out. Clear it out, new problem. So 4,324,000 times 1 minus 0.11 raised to the 7th power. And right there, that's 1,912,000. 562.9. So let's round up because we're talking about people here. So 563. All right, people who are illiterate. It'd help if I spell that correctly. So illiterate. Okay, there we go. That's bad. I mean, still, even though they put this new incentives and funding and everything to help people read and write, there's still almost 2 million people illiterate after 21 years, which is really bad because, we want our society to be fully functioning, right? All right, but how about, in the year 2095? So 2095 minus 2014, we get 81 years. So T in this case is 81 divided by 3. You know what that is? 81 divided by 3, 27. So 27 time periods. Okay, so let's figure this out. We start off with 4,324,000 literate people. We got to multiply it by 1 minus 0.11 raised to this time 27th power. No big deal in the calculator. 4,324,000 times 1 minus 0.11 raised to the 27th power. No big deal. Look at that. 185,958. People, illiterate, illiterate, there we go. All right, people. Now that's not bad, we can handle that. less than 200,000 people after year 2095, if this can actually be done. They predict that, but you know, what they predict is not always what happens in reality. So it's always their best intention, but who knows? All right, so let's take a look at this one. Number 7 here. How many do we have to do? 9. Okay. So number 7, sub-Saharan Africa, or in sub-Saharan Africa, an estimated 28.5 million people are infected with AIDS. Whoa. Wow. That's amazing. Unfortunately, that number is rising and is estimated to grow at a rate of 0.4% every 2 years. So right here, this is a growth rate. So automatically, I know I'm dealing with this situation here. 1 plus r, or a sub I, times 1 plus r to the t power. I know that r is 0.4%. And just do the math here. 0.4 divided by 100. All right, it's 0.004. So 0.04. Be careful right there. It's a growth rate. And look under this, underline this, every 2 years. That's the number of time periods, or our time period right there. Okay, so here, the t value here is that I know it does this, or it grows every 2 years. So after 3 years, the question is how many time periods? Well, it sounds like kind of 1.5 time periods, right? Every 2 years plus another one equals 3. So 3 divided by 2, 1.5, 1.5 time periods. All right, I've been doing this every single problem. And so get used to this. I do this first before I even solve the problem. So what do we have? 28.5 million. Now 28.5 million. Let me convert this. 28.5 million is this. That's 28.5 million. This equals 28.5 million. All right, so let's put that number in. So 28,500,000 times 1 minus, or excuse me, plus, this is a growth situation, plus 0.004 to the 1.5 time periods, okay? So let's put this in. 28,500,000. Let me see here, double check here. Looks right. Times 1.004 raised to the 1.5 time periods. So now there's 28,671,000. Okay, there's more. All right, so 28 million, what did it say? 671,171. 171 people infected. All right, this is obviously bad. Oh, because, you know, it spreads so fast. Now, how many people in Africa are going to be infected after 10 years? Well, t is equal to 10 divided by 2 now, because again, every 2 years it does this. So how many time periods? Well, after 10 total years, 10 divided by 2 would be 5 time periods, or intervals, right? So my future amount in this case would be 28,500,000 times 1 plus 0.004 again, but this time to the 5th power, because there's 5 time periods over 10 years. All right, just think about this. 2, 4, 6, 8, 10, 1, 2, 3, 4, 5 periods. All right, that's what this number 5 represents. Okay, so what does that equal? I don't know. Let's figure it out. As I keep on saying in all these problems here, gotta make sure you put the right amount of zeros in here. All right, times 1.04. Oops, that's incorrect. Go back. 0.04 raised to the 5th power. And look at this. In the future, there's going to be over 29,074,000. So 29,074,578. So 578 people infected. It's getting worse. That's why they call this an epidemic. All right. You know, it's a huge problem in the world. And after 1,000 years, what's going to happen in Africa? Well, God forbid. All right, so after 1,000, so 1,000 divided by 2 is 500. So 500 time periods. So how many people? Well, let's figure it out. So 28,500,000, all right, times 1 minus 0.004 raised to the 500 power. This is O plus. This is not good, guys. So 28,500,000 times 1.004 raised to the 500 power. Not looking forward to this number here. Okay, so here, every 3 digits, so 200, 9,749,000, 660 people. All right, that's a lot of people, and I don't know how many people in Africa. We'd have to go research that, but that's a huge number of people, guys. And that's a really bad situation. I don't think you want to be in Africa with this kind of epidemic going on. All right, number 8. Over the last several years, there has been an increase, obviously an important word, in the amount of school-age children carrying cell phones. Oh my God, this could be referencing you guys. In the year 2014, it is estimated that there are 1,237,000 students in the U.S. with cell phones. That's an A sub I, isn't it? So A sub I is 1,237,000. That's the initial amount in 2014. So let me make reference to that. The trend is likely to continue, and the amount of children with phones is tripling every 3 years. Tripling. Okay, that means base 3, right? If it triples, it increases by 200%. So it's an increase, okay, of 200%. All right, and that's the growth rate. So the growth rate right here, R is growth rate. Let me fix that. The growth rate, R, is 200% or equal to 2. And so when I add 1 plus R, I get 3, which is the tripling, okay? Now let's highlight this, every 10 years, that's important. So what's happening here after 10 years? Well, we're in 2014, so 2024 minus 2014, that's 10 years. So in this case, T is 10 divided by 10, which is 1 time period. So it triples every 10 years. So after 10 years, there's only 1 time period. It triples. So here we go. The amount in the future is 1,237,000. All right, times 1 plus R, which in this case is 2, first power. It triples every 10 years. So in this case, it's 1,237,000 times 3. So let's just work this out on the calculator here. Let's clear it out. It's a new problem. 1,237,000, all right, times 3. It triples. So 3, well, I didn't type that incorrectly, I don't think. Yeah, 3,711,000. So 3,711,000 total cell phone users, all right, people that are students using cell phones. So students using cell phones. And we expect that number to increase here. So how many by 2029? Well, let me see, 2029 minus 2014, that's 15. 15 years have gone by. Okay, well, T in this case is 15 divided by 10 because every 10 years this thing triples. That's 1.5 time periods. So what's my future amount? Well, I've taken a 1,237,000 times 1 plus 2, because remember, this is base 3. This is a tripling problem. So it's going to be base 3 here, raised to the 1.5 power. So what is that? So 1,237,000 times 3 to the 1.5 power after 1.5 time periods. Check this out, guys. There is 6 million, excuse me. Yeah, 6,427,000. So 6,427,641. All right, students using cell phones. So students using cell phones in school, which is a lot. Okay, good. So we can communicate with you guys, but create some problems. All right, don't need to get into that. All right, last problem. Here we go. Coal was once a booming industry in central Pennsylvania. However, in the industry has begun to decline. Ooh, decline, underline that. In the year 1950, there were 600,000 were employed in the local coal mines. See right there? That's A sub I. All right, in 1950. That's the reference year. Since then, the number of coal miners has declined, gone down. All right, this is a decay situation. Okay, that tells me that I need A sub F equals A sub I times 1 minus R to the T power, because this is a decline situation. I said it twice. Okay, declined by how much? Well, what's the decay rate? So right here it says 5% every 6 years. So R is equal to 0.05, all right, every 6 years. That's important. Let's highlight this, every 6 years. So here we go. In 1962, that's 12 years past 1950. Remember, that's a reference year. So 1962 minus 1950, that's 12 years have passed. So in this case, 12 divided by 6 is 2 for 2 time periods. Notice that I calculate the number of time periods in every single example, even before I start the problem. You need to do that on all these problems. So here we go. We take the initial amount, which is 600,000, times 1 minus, it's a minus because it's a decay problem, things are declining or going down, minus 0.05 or 5% raised to the second power. Let's figure this out. Clear it out, it's a new problem. So 600,000, okay, times 1 minus 0.05 raised to the second power. And you get about 541,500. 541,500 coal miners. Okay, when it started off at 600,000, now it has less. Why? Because it's declining by 5% every 6 years. Probably because of the advent of machinery. Okay. Now on this next one here, how many years have gone past from 1950 to 1980? And the obvious answer is 30 years. So in this case, we take 30 divided by, again, every 6 years. Right here, there's a key number here. 30 divided by 6. There's 5 time periods. So in this case, my future amount is my initial 600,000 times 1 minus 0.05 to the 5th power now. All right, so I take 600,000, check to see if you inputted it correctly there, times 1 minus 0.05 raised to the 5th power. And I get about 464,268. 269. So 269 coal miners. Okay, well, last one. How about in 1992? Well, in 1992 minus 1950, there's 42 years have passed. So in this case, it's 42 divided by 6, or 7 time periods. So last one, we take 600,000 times 1 minus 0.05 to the 7th power. So 600,000 right there times 1 minus 0.05 to the 7th power. and I get about 419,002. So 419,002 coal miners. After 7 time periods, or after 42 years. And there you go, guys. This is how you use your growth and decay functions to your advantage, solving all kinds of cool problems here in real life. And this happens all the time. And I bet you never thought that mathematics can be so applicable to real life, but it is. You just need to learn enough math to figure it all out. And this is a good taste of it. All right, remember, this is a video. You can always rewind and go back to any problem you want. And remember, this one thing watching and doing things with me, it's another thing doing them by yourself. So work really hard, practice the problems, and get good. And I'll see you in my next lesson. This is Mr. Ainsworth signing off. I'll see you then.